In this problem, we're asked to calculate the pH of a solution containing a weak base. Remember that bases react with water, not merely dissociate. So we're going to represent our base simply as B. It's going to accept an H plus from water to give this conjugate acid. And what's left behind is a hydroxide ion. Kb is then equivalent to OH minus and our conjugate base, conjugate acid, divided by our equilibrium concentration of our base. Ice table. Water is a pure liquid. We don't care about its concentration. It doesn't appear in K. So we have 1.5 molar. None of the initial of the conjugate acid or hydroxide to start. We lose X off the base, gain it in our products. Initial plus change is equilibrium concentration. We can make our substitutions. To employ the method of successive approximations, we'll solve for h squared. That's our highest power of x. Because x is going to be the square root of x squared. Take as our initial value x sub 0 is equal to 0. We get x1. And our initial value of x is 0.0297. x2, our next approximation, is obtained by taking this value and plugging in for x. We get our value of x2 is 0.0295. Okay, so we see that there's essentially no change within significant figures between our first and second approximation, and that means that this x is negligible compared to our initial concentration. Alright, so we have, we can continue this a couple different ways. I prefer to solve for POH as our negative log of hydroxide ion and we get our value of 1.53, 2 decimal places since we have 2 significant figures in our problem, and pH is thus 14 minus POH since we're at 25 degrees C, and this would be equal to 12.47. So a weak base problem is really no different than a weak acid problem, with the exception that we end up solving for hydroxide ion concentration and such, so there's an additional step.